Hello, we are Greece United, our official name for the competition, but we like to be called Nous. So watch out and don't mistake us for somebody else or for a football team.
Nous is an ancient Greek word translated as brain. A general definition describes nous as a set of cognitive abilities such as consciousness, perception, thought and memory. On the other hand, nous in French literally means we. We seek to act as a unity through communication, which is our keystone. So the word nous, apart from characterizing the strength of each one of us separately, also describes the spirit of the team as a whole. We started off with 5 initial members in 2019 and went through the process of applications and interviews to expand our team. Currently, nous consists of 12 students who study in the departments of molecular biology and genetics, biology, medicine, computer science, physics, economics, computer science and biomedical informatics, and graphics design. Our team members are distributed across Greece in 4 different cities and 6 different universities. Our headquarters lie in Alexandroupoli, a city in the north of Greece, where we had the opportunity to develop our work under the roof of the Democritus University of Thrace. Professors and associates from the university staffed our team as PIs, advisors and instructors that guided us all through our course. In Greek mythology, Epione was the wife of Asclepius, the god of medicine. Her name derives from the word Epios, that means soothing. She was not a goddess herself, but she was the personification of the care needed for recovery and healing. Setting this meaning as a goal, we named our project Epione, because that is what we strive to do: soothe and solve one of the greatest and most persistent health problems of our modern world, osteoarthritis. We designed a simple approach to end the suffering of osteoarthritis patients once and for all, by reversing the problem and fighting its source instead of only the symptoms. We are not gods, but we hope that one day our cure will be able to drastically change the lives of millions in need.
But first things first, what is osteoarthritis? Osteoarthritis is a degenerative joint disease characterized by the progressive destruction of the articular cartilage and, in later stages, the entire joint, including the synovium, the ligaments, and the subchondral bone. It results in increased friction between the bones, causing dyskinesia, stiffness, and pain. In advanced stages, it can cause paralysis as well. Osteoarthritis affects 7% of the world population. It is one of the top 10 causes of paralysis in developed countries. One estimate of the lifetime risk of developing symptomatic knee osteoarthritis was approximately 40% in men and 47% in women. Although it is a condition associated with advanced stage, it can occur in children and young adults, while obesity or injuries increase the risk. At the same time, as the average life expectancy rises, the percentage of people with some type of osteoarthritis will rise by 45% until 2050, managing to affect approximately 90 million people and leaving 40 million people severely disabled. On the other hand, the overall economic burden associated with osteoarthritis in the US is estimated at $136 million annually. This number is not exclusive to the US, as osteoarthritis has a global impact as demonstrated above. For perspective, the annual economic cost of arthritis surpasses that of cancer. Now that we have your attention, let's dive into the biological details of osteoarthritis. Disclaimer: the detailed molecular mechanisms that initiate and help osteoarthritis progress remain unclear till today. However, osteoarthritis is characterized by progressive deterioration of the articular cartilage. Articular cartilage destruction is caused by degeneration of the extracellular matrix, mainly composed of type II collagen and aggrecan. The progressive deterioration of the articular cartilage is caused by degrading enzymes, metalloproteinases MMP14, ADAMS4 and ADAMS5, and by pro-inflammatory cytokines IL-1 beta and TNF-alpha that cause an inflammatory cascade. Sadly, there are no interventions available today to restore degraded cartilage or decelerate disease progression.
What did we do about it? In our pursuit for a cure for osteoarthritis and the hope to put an end to this inflammatory cycle, we decided to use a genetic circuit which can sense inflammation. This genetic circuit can sense inflammation by binding the NFKB molecule, a transcription factor overexpressed during inflammation. This genetic circuit consists of 5 parts. The first part is the sensor. Its role is to detect NFKB and allow through its binding the activation of the circuit by producing Gal4-VP16. Then, GAL4-VP16 can bind to the amplifier, whose role is to amplify the signal by producing higher amounts of GAL4-VP16. Eventually, the GAL4-VP16 molecule will bind to the promoter of the effector, activating the expression of the genes that follow. This whole genetic circuit is accompanied by a thresholder. The thresholder's role is to ensure that the genetic circuit remains inactivated when minimal amounts of NFKB are present. This can be achieved by the production of GAL4 in low amounts. GAL4 can bind to the promoters of the circuit without activating their expression. For the genetic circuit to be activated, the concentration of the NFKB molecule needs to surpass that of the GAL4 molecule. Next component is the safety switch, or else the repressor. It is responsible for the production of the RTR-KRAB molecule. If left alone, this molecule will degrade fastly without affecting the genetic circuit. However, the whole genetic circuit can be inactivated by the insertion of doxycycline in the system. Doxycycline binds to the RTR-KRAB molecule, enabling it to bind to all of the promoters of the genetic circuit and therefore inactivating the circuit.
After some more research and some thoughts, we started considering the use of exosomes and microRNAs in our approach. For that purpose, we contacted Professor Dr. Skretas, who is an experienced synthetic biologist, to discuss microRNAs and how viable this approach really is. Concerning the exosomes, we knew that they are widely being used as a diagnostic tool for many diseases, but they had rarely been used as a therapeutic tool to deliver certain molecules into certain cells. Researching, we found out this is a brilliant and functional idea, but not well studied, creating a considerable research gap, which we aim to minimize by using exosomes as a transportation vehicle for our therapy. Therefore, we needed the opinion of someone experienced on using the exosomes, and we contacted the PhD candidate from Heraclion, Crete, Mr. George Niotis. We discussed technical details about using exosomes, and he shared with us some of the fundamental mechanisms of how exosomes are formed. After researching and consulting experts, we concluded that the genes in the effector would be responsible for the production of exosomes that would target specifically chondrocytes and transport a microRNA, in particular microRNA 140. To make sure that the produced exosomes would directly target the chondrocytes, we used a chondrocyte affinity peptide. This peptide was fused to the protein LAMP2B, a transmembrane protein found in the membrane of exosomes. Therefore, the chondrocyte affinity peptide would be on the surface in order to target the chondrocytes. Besides that, we fused the LAMP2B with the GFP protein, aiming to detect and quantify the exosomes produced by the cells. We also needed to include the precursor sequence of the microRNA 140 in the effector in order for the microRNA 140 to be produced by the cells and to be included inside the exosomes. MicroRNA 140 is a microRNA normally expressed in high amounts in chondrocytes and is responsible for the cartilage regeneration. In osteoarthritic chondrocytes, the levels of the microRNA 140 are downregulated. However, it has been observed that by overexpressing the microRNA 140, the progression could be stopped. More specifically, it can downregulate the expression of metalloproteinase 13 and ADAMTS5, which would decrease the degradation of the cartilage and the inflammatory cycle would be altered. After some more research and some discussions with our PI, Dr. Mardzikova, we concluded that transfecting a single cell with 5 different plasmids, as each part of the genetic circuit is incorporated into one plasmid, is something very difficult to implement. Therefore, we decided not to include it in our laboratory experiments. Instead, we decided to test only the part of the effector. The rest of the genetic circuit would be simulated to fully understand its behavior and functionality. Mesenchymal stem cells are already being studied as a potential therapy for osteoarthritis, so they seemed ideal for our circuit. They are indeed beneficial for an osteoarthritic joint as they promote the regeneration of the cartilage and the differentiation of chondrocytes. But
Bearing in mind the difficulties of cultivating and transfecting this cell type, in combination with the restricted time we had available, we decided to work with the more common cell type, the human embryonic kidney cells 293. Unfortunately, during our experiments, our team was not able to assemble the genetic construct in order to transfect the HEC293 T cells and quantify the produced exosomes with the microRNA inside them. However, very meticulous simulations were built by our dry lab team in order to analyze in detail the whole system and give us an estimation of how this plasmid would be expressed.
To achieve that, we built two different models concerning the genetic circuit and the production of microRNA carrying exosomes. Let's start off with the genetic circuit model. The model utilizes species such as genes, proteins, and complexes. A protein binds to its corresponding gene via its promoter, forming a complex. Then the formed complex produces the product of the gene, which in most cases is a different protein or the effector itself. The lines that connect the species with each other are reactions represented by mathematical equations. These reactions either represent a heterodimer association, dissociation, or a state transition. By separating our model into compartments, you can clearly see each part of the genetic circuit represented here, like the sensor, amplifier, thresholder, repressor, and of course the effector. This model came as a solution to the time problem of transfecting 5 plasmids. We wanted to determine whether we could exclude some parts of it in order to reduce the number of plasmids while maintaining a significant amount of its functionality. In a different turn of events, we would use the simulations of the genetic circuit to demonstrate how this solution would function in real-life conditions. Moving on to the exosome production model developed in both Cell Designer and the C++ programming language. Let's begin with the Cell Designer part of the model. This one is a bit different from the genetic circuit model. The species that form this model are genes, proteins, RNA molecules, and complexes. It starts off with a gene and a transcription factor that form a complex, which in turn produces an RNA molecule. This RNA molecule is then split into two parts, the pre-microRNA and the mRNA molecule that is translated to the LAMP2B cap exosome protein tag. Those two are then loaded into the two different types of exosomes, the cap and the non-cap containing exosomes, which are also the final product of our circuit. This model allows us to calculate the amount of cap and non-cap exosomes produced by a single cell and the time span that the cell will be producing them for. It is important for us to calculate the number of cells needed for an effective cartilage repair, as well as how often we will need to replenish those cells.
The idea for the second model is similar to the previous one. The only difference is the method used for the simulations. That means that the equations and the constants that are used are different, though they still describe the same phenomenon. We constructed an Ode model developed in C++ code language that is parted from several variables and constants that are used to complete the ordinary differential equations we developed. It simulates the behavior of one cell transfected with one plasmid. There is an equation describing the rate of change of the concentration of every substance partaking in this process. The current value of every element is determined by the addition of the value in the previous moment and the current rate of change in its concentration in a fraction of time, 1 minute. That results in the total concentration up to that moment. After gathering the results for one cell, we calculated what 1,000 to 5,000 similar cells would do. The results are promising and show that by introducing our therapy in its current design, cells will be affected in the whole target joint by a sufficient number of exosomes that will introduce a significant amount of microRNA in each cell. Based on literature data, our results show that we have sufficient therapeutic potential.
By connecting these two models together, we even managed to see how the system would have worked if we were to have used the genetic circuit. It helped us get the full picture of our idea and provided valuable information like how effective the circuit would have been in different NFKB levels or the difference between cap and non-cap exosomes produced.
Epione's daughters were symbols related to health as well. ESO symbolized healing, Panakia was cohesive with any cure, Hygeia literally means health, SSO derives from an ancient Greek verb meaning heal, and Negli represented robustness and pristine health. That is the name we gave to osteoarthritis risk factor calculator. EGLI is a calculator that uses medical evidence from recent high-level medical publications to help the public perceive the risks of osteoarthritis, enhance health literacy and disease awareness, and help doctors better understand the diagnosis of this disease. Our app is based on the CARE Health Risk Ontology, an EU FP7 ICT project, and expands the CARE Health Risk databases in the field of osteoarthritis. The code we developed is accessible online and open source as an effort to encourage future researchers to expand and use our tool in any case it is relevant. A web page with a friendly and comprehensive user interface is created dynamically based on the risk factors available. Once the user inserts their data, the risk estimation is produced in the form of a bar diagram.
We envision our proposed implementation brought to life in a manner responsible and good for the world. To do so, we plan to work with the World Health Organization, the government and pharmaceutical companies, three important stakeholders that play a significant role in implementing Epione to the real world. To begin with, we identified the major safety risks and developed a plan to overcome them. After the competition, further research and development is needed to elucidate whether the increase in local expression of the gene selected for the effect leads to a malfunction or abnormality, but also to minimize the potential risks due to the delivery method of the therapy. Finishing with the research and development plan, Epione will continue its journey of reaching the market by entering the clinical trials. First, preclinical research must be done, which consists of laboratory and animal testing to answer basic questions about efficacy, toxicity, and pharmacokinetics. The next big step is to surpass clinical phases 1 to 4 in the years to follow. Once Epione is eligible to enter the market, the therapy will be administered in a simple way. The patient is diagnosed by the doctor. Then the doctor extracts mesenchymal stem cells from the patient and the cells are delivered to the pharmaceutical company for therapy preparation. There, the genetic information will be inserted into the patient cells and the screening is required to isolate the transfected cells. After that, the cells are delivered back to the doctor who prepares and injects them into the target joint. Ultimately, the cells could be delivered transdermally via an appropriate wearable patch. Our proposed implementation wouldn't be possible without building a solid business plan. To do so, we reached out to numerous business analysts, strategists, stakeholders, and capital investment companies to discuss, seek advice, and consult. Also, we were one of the few teams selected to participate in Archimedes Business Accelerator, in which we are actively enrolled since February. Thanks to the mentoring and experienced guidance we received as a team, we were able to elaborate an analytical market analysis while at the same time calculating meticulously the strategic planning. Two key components of our business plan that showed a great future for Epione and also great opportunities in a long-time fixed market. Finally, on our way to implementing Epione to the real world, we contacted and presented our work to pharmaceutical companies such as Novartis and Elpen, but also Demium, a Spanish talent investor company from which we have received a letter of intent in order to participate on their business accelerator program and then continue with their pre-seeding and seeding program, getting the necessary funds for preclinical trials.
Our project, though, expands beyond the lab and the entrepreneurial aspects of it. We had a constant interaction with the society, trying to teach but also learn from it. Before initiating any communication materials and events, we aim to deeply understand the state of knowledge and opinion of our community. Our primary goal was to get a valid and up-to-date view of the public information status about basic biological concepts, as well as views on synthetic biology. To achieve this, we conducted a survey in the form of a questionnaire, targeting many different age and socioeconomic groups. Using the results of this survey, we developed and customized our activities to have a significant impact on the public that is not well informed, as shown by our data. We thought of this as part of the wider cycle of scientific thought dissemination and managed to combine actions and activities to cover the need for information. Our first action included educational videos openly shared on YouTube to ensure accessibility for all audiences. To support and enhance this effort, we actively use social media for informative purposes by posting facts, quizzes, and initiatives like Pick of the Week, but also as a means of direct communication with the public. The asynchronous internet, though, is not enough. We felt that something more immediate was needed. A series of more targeted and engaging activities we conducted, such as Lab on the Street, an initiative that engaged more than 60 people, adults, youth, and teenagers, in biology experiments and discussions, showing remarkable interest and excitement. As an addition, we organized special webinars targeting different groups such as scouts and high schoolers. The culmination of our need for the common good was the sea organization of simultaneous blood donation events in two different parts of the world, Greece and Korea.
To further initiate participation in science and enhance accessibility, we created a web platform that meshes educational tools such as a comic book, digital word games, and instructional slideshows. These aim to provide a holistic educational experience for collaborative learning and teaching in heterogeneous learner groups, including learners from different levels spanning from kindergarten to high school and higher education. The combination of different educational activities and instructional models creates the perfect environment for parents or educators to learn together with their children while engaging in fun activities. We have used the portal in many of our educational activities to spark discussions with the audience and engage them in entertaining educational sessions.
As a team, we vow to remember, encourage and engage those who are commonly forgotten and dismissed. Studies have shown that women feel empowerment in single-sex learning environments where socializing and peer tutoring are achieved easier. Failure to provide that results in lower grades and less ambition. Hoping to do our part in the establishment of a solution to this injustice,
We organized a 4-day biology webinar to inspire and encourage young girls to pursue science. BioGirls not only provided knowledge about synthetic biology to little girls, a field that is not included in the Greek school curriculum, but also gifted them the belief that they can be anything they may wish.
Unaccompanied refugee kids, during the usually long wait before they are reintegrated into society, have less opportunities for education and engagement in science. We created a biology comic book and distributed it to our local shelter to inspire, entertain, and educate young kids. We also had the chance to meet those kids, present our team and our project, and teach them about synthetic biology. A lot of dreams were born within this team, a lot of hopes were fulfilled, and expectations were met. We hope to furtherly advance our project in the future to provide one less painful step. We would like to thank all of our sponsors, without whom none of this would be possible.